In this video, I want to teach you how to do shorthand electron configurations. You should already have practice with making the longhand electron configurations. At this point, these are all the things that I'd like you to know before watching this video. You need to know what the four principal quantum numbers are and how they apply to orbital and electron configurations. You need to know about the sp, d, and f subshells, and then also remember this figure with the stair steps on the bottom right. That is going to teach you about Aufbau's principle, and remember all it is doing is teaching you about energy and the amount of energy that's required for each subshell or principal quantum number. So meaning if you enter an electron into the 3p orbital, you go next into the 4s orbital as opposed to the 3d orbital. So knowing all that beforehand, let's talk about shorthand electron configurations. All right, you already know about how we can look at the periodic table and cheat, if you will, to help identify electron configurations. And so this type of configuration is your hand gets tired of when writing those electron configurations of writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And so is there a quicker and easier way to write all of that information? You know scientists love some shortcuts, so absolutely there is. And so this configuration, the shorthand electron configuration, is also called Nobel Gas Configuration because we are going to look specifically at our noble gases. So remember, here are all of your noble gases in group 8A. And so what's going to happen is with all of these right here, these are our extremely stable elements. And as such, they have filled orbitals, which means hydrogen has 1s1. It's not filled because the s needs to have or would like to have 2 electrons in its subshell. And so helium does have a stable configuration. Its 1s is completely filled. Neon, it has 2 electrons in the 2s and 6 in the 2p. So both of these subshells are filled entirely, and so they're extremely stable. So what's going to happen is all of these other elements, since they want to have stable electron configurations, we're going to represent them like noble gases, and we're going to compare them to those. And so magnesium, what is the noble gas that's prior to magnesium? So if you just go backwards, magnesium, sodium, and then you make it here to neon. Neon is the first noble gas immediately prior to magnesium. If I come down here maybe to germanium, I have to go all the way back, all the way back through all of these elements to get here to argon. And that's okay. You don't go forward, you go backwards. And so what do I mean by that? Germanium, let's do that. It has how many electrons if it's neutral? 32 electrons because that's its atomic number. And so if we use this cheating way of filling in electrons, our electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. After 4s2 comes 3d10, and then 4p, and notice there's only 2 electrons in 4p, so it's partially filled. Next, we need to identify which of these electrons belong to argon, because I almost ran out of room. Wouldn't it be nice to write this a whole lot more simply? And you can. So argon, its last electron is in 3p, which means all of these electrons also are in the argon electron. And so we can represent this by putting a bracket of argon, and basically we're saying, hey, you know all that stuff that's in argon? It's also in germanium, which it is. And then we can put all of these remaining electrons next to it. So now I need to fill in all of these electrons down here. But remember, all of these electrons are not written in numerical order, they're written in energy level order. So meaning 4s has less energy than 3d, and 4p has more energy than both of them. We need to rearrange these in numerical order. So we write 3d10, and some people won't choose to do this. It's a matter of preference a little bit, and I think it's a measure of practicality. What do I mean by that? Well, which of these are my valence electrons? I hope you said these. These are basically the ones that are going to be involved in this class in bonding. And so what I do know here is this 4s2, 4p2, those are the same number of valence electrons I have in my 4a group. And so what that tells me is that germanium is going to be involved a lot in covalent bonding, as opposed to those that are in like 7 that need 1 electron to become stable, therefore it's going to form chlorine ions. And so this type of shorthand configuration is a simple way of allowing yourself to look at it quickly, see those valence electrons here, and then make decisions about bonding. Let's do another example. How about iodine? That's a huge one. So iodine has 53 electrons in its energy levels. So iodine, what are we going to do? Let's write the electron configuration. If you want to stop the video, do it yourself and then come right back. It shouldn't take too long. 1s2, 2s2. You notice I'm writing really small because we got a ways to go. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and I'm out of room. Don't I wish there was a shorthand way to do all this? So after 5s goes 4d10, and then 5p, and there are 1, 2, 3, 4, 5 electrons in the p shell. All right, so then what about my shorthand? What is the noble gas that precedes iodine? And we know it is krypton. So we put Kr in brackets, and I know that stands all the way up to the 4p subshell. So these electrons are already included in krypton. What comes next? Reorder them numerically so we can see our electrons. 4d10, 5s2, 5p5. And that allows me to see that I have 7 valence electrons. Let's do another example. How about a simpler one? How about sodium? Na has 11 electrons. So Na has an electron configuration of 1s2, 2s2, 2p6, 3s, and how many electrons? 1. It's the first electron here. So is there a configuration that we can do for shorthand? Absolutely. Go that direction and you hit neon. So neon is my noble gas. What's included in neon? All of these electrons and 3s1. I know I'm doing this pretty fast now, so feel free to kind of pause it at any moment that you would like and work through it. You'll be this fast before you know it. What about krypton? We haven't done a noble gas yet. So 36 electrons. So first write the electron configurations. 1s2, 2s2, 2p6, and sometimes it helps me to kind of keep my hand on krypton so I can see where I am going. 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6. All right, now this is where it's tricky because it is a noble gas. Can we just write Kr? And sometimes I see that, but most of the time I will see it the opposite. What do I mean by opposite? Instead of just representing Kr, because that's not as helpful, you will do the noble gas prior to it. And so we have argon in brackets, followed by everything that is not already in argon, which is all of these electrons, putting it in numerical order. And we have a completed shorthand electron configuration. Let's do one last one together. I know a little bit of extra practice is always very helpful. How about another easy one? Let's do boron. That has 5 electrons. 1s2, 2s2, 2p1. The noble gas immediately prior to that is helium. Helium has a 1s in it. And so it's going to be helium and then 2s2, 2p1. Make sure I can tell which ones are superscripts, and which ones are coefficients. And that is how you do shorthand electron configuration.